Let's start the talk. I like to start with this sentence from Bin Luo about 1 year and a half ago, where he said there was a time in which people did not believe photometric redshift for AGNs. We have demonstrated that actually they can be reliable. We have learned a lot in the last 10 years. And in particular, from my point of view, at least what I've learned, I learned it all on the cosmos field, because it is including deep data in every band, where bands include broadband and intermediate bands. It is a large field, so that you have the bright rare objects and also the faint deep that are, and the bright are normally missing from other surveys. And the photometry is done in an homogeneous way such that it is really easy to change the parameters and see how your parameters are affecting your results. So all what I've learned essentially using Cosmos. I would suggest that if you are having some testing, Cosmos should definitely be an ideal field to use, also because the data are public, and including the spectroscopy, which is very rich. The structure of my talk is the following. I am going to give one slide that represents my recipe of how I compute Photoz for AGNs, and then I would like to go through the relevant steps, and I am highlighting with an underline the points that I think are also very important for LSST. And maybe this talk is too rich of information. I do not know how many of you are familiar with all what I'm going to say. Maybe some maybe found it even boring. I do not know. And I do not know whether you prefer that we stop to every slides and we discuss it, and maybe breaking the talk in 2 parts, or I just go on with the talk and then we have questions at the end. In any case, I can give you the slides at the end, so you can keep it and you have actually the recording. So maybe, I don't know, Roberto, what you prefer. Maybe people can interrupt me as soon as they see something unclear, rather than get confused and then losing track of what they wanted to ask at the end of the talk.
Yeah, absolutely. I think that's preferable, if that's okay with you.
Absolutely, no problem, absolutely. Good, so let's start. My recipe, this is what I do usually. I start from a sample of normal galaxies, non-AGNs, with spectroscopic available, reliable spectroscopic available, with the same photometry data set that I'm going to use for the AGNs. And I compute the 0-point offset, making use of a library of normal galaxies. Already, this was demonstrated back in 2013 in a paper that Thomas Talent led, where we have shown that the best Photoz's were all computed by codes that included a 0-point offset in the analysis. This is particularly important in days in which the photometry is not homogenized like it is for Cosmos or candles like in that paper, but is simply a match in coordinates between different surveys where the photometry is computed even in different ways. Just think Cron, Petrosian, model, and aperture, different aperture, and so on. So this is really important to rescale or calibrate the photometry, even if it does not have a physical meaning. Then I need to correct for variability, and I will discuss this point later. And I will apply my 0-point offset on the fly. It's not going to be applied to the photometry. When I have then this photometry done, I separate my X-ray AGN sample in 3 subgroups. Here, first I isolated the sources that are varying or are point-like. And for those sources, I definitely am expecting that the AGN is the dominating component. And that's why I am running templates of AGN, quasars, and hybrids, where hybrids are galaxies host plus AGN component. And what I'm using is a prior in luminosity expressed as absolute magnitude that is typical for AGN and quasars. So I'm using the Veron and Veron old definition, saying that AGNs and quasars should have an absolute magnitude between -20 or -30. In this way, if there are a low redshift solution, they are completely dropped. When you have then the extended sources in the optical, you have two families of objects. There are those that are a bright X-ray source. I forgot here to write the number, I apologize, but it is in my papers. These objects are the Cipher ones, like the Cipher 2 object that have a 50-50 light coming from the host and from the AGN component. And here again, I have AGN quasars and hybrids. And this time, the absolute magnitude is typical for normal galaxies between -24 and -8. And then I have the third group, which you have still extended sources, and the X-ray luminosity is extremely limited, and these objects are definitely dominated by the host galaxy, and that's why I'm using the same templates that were used when I compute the 0-point offset. And then at the end, I merge the catalog. So this is the recipe that I am using. And then I can go on each of these ingredients and see how I choose my threshold, my structure. Again, tell me if you want to, if you have questions. Just to tell you, I forgot already one component. You know that I am running my work on Rosita now. We have already the first 140 square degrees at the final depth of Rosita, in addition to have the first all-sky survey, and we are going to make a press release tomorrow. Stay tuned. On the Rosita IFES area, I have 22,000 normal galaxies, and if I compute the photosys without a 0-point offset correction, the sigma is 7% with 6% outliers. But as soon as I correct for the 0 points, I have, as it should be when you have broadband photometry, a sigma of 3% and only 3% outliers. And I would like to remind here that, for example, for Rosita, we are only using broadband photometry.
Can I ask a question?
Yeah, please.
Do you get any overlap between these different categories so that you can control for systematics between the different prescriptions?
I do it by hand, in the sense that I run for everything, and then I see if the cutting is, the separation between the groups makes sense. So I didn't have a slides on this point, but I thank you for bringing it up already. One of the big problems that we have is the separation point-like and extended. Because depending on the photometry that you are using, you are getting different results. So in the Xu et al. Paper, we actually have a section about it, and we have shown that 30% of the objects that were considered extended in in Hubble images were actually point-like from ground, just because the blurring of the PSF. And so putting this object in the wrong sample then was providing the wrong redshift. And similarly now, the problem that you have is to define the point-like sources. And normally what you do, you compute the difference between the Cron magnitude and the model magnitude, and you have to decide the threshold, and you also have to decide the band. And do you use all the bands that has to be point-like at the same time, or only the red? So this is creating some uncertainties. And a lot of time is spent in tuning that. If you then consider that the result that you get is always based on the spectroscopic sample that you are using for making this evaluation, it can be a little bit unsecure as a result. So there is a margin of uncertainty in that point, yes.
So how faint in an optical band are these objects?
They are usually, how big is on ground-based observation an object redshift 0.6, 0.7, 0.8.
Okay.
Normally the extended is normally done from the stellarity, you know. So there's the stellarity equal, so objects that are not considered, so objects that are extended can be, that if they are very nearby, sorry, go back. It depends also on the survey that you are using. If you are having a very extended wide survey, extended can also be an object at redshift 0.1, so gigantic, because you have the
Sure.
rare and light object. So it's really a varying dimension. But I will call the one here an extended, and this one is a point-like. And but these are HST images. So in the optical, they are slightly less obvious to see.
Yeah.
Now,
if they're bright enough, you can use things like wise colors to sort them out, but that won't work past about 20th magnitude.
Exactly. So this is one of the problems. So it's really the tricky part, and probably there I have to do some improvement still. Okay, so then I move on the first ingredients in my template. So I try to give some slides on templates. Our templates are empirical, and it means that they have been already absorbed through the intergalactic medium. Now, if you're using a code like me using LEFAR that has intergalactic extinction correction built in, and there is no way to turn it off, if you're using an empirical template that has been already absorbed, once that you put it within LEFAR, is going to be absorbed once again, and the fit on the blue part of the spectrum is never going to be good. So what you do, or what I have done, is taking the objects, you extend the continuum before the Lyman alpha and add a power law using this slope from Scott et al. That obtained by Fuse service of AGNs. And then you can see in my templates for all the objects that are dominated by the AGN, type 1 and quasars, you always see this line, and that is the reason for it. The second part, yeah?
Sorry, it was a more general question, maybe not to you, but do we actually know what the change in the UV slope is as a function of accretion rate and black hole mass?
I think it is kind of constant. I mean, normally you have, the templates are pretty similar in every redshift, right? I know you said as a function of accretion.
I mean, effectively AGN luminosity, right? But for a given black hole mass.
Yes.
But
it is a function of luminosity. I mean, Telfer has a very different slope.
Yes.
Right.
But why don't you? Why don't you just? Why aren't you just adding back in whatever the fair is taking out?
This is what I'm doing.
Okay, the fair is assuming the Scott power law.
So I'm adding really a power law that is taken as an extension from the continuum. So using this slope is really, yeah, this part here.
Well, the fair isn't assuming anything.
Assuming anything. So this is a sample of, I don't know, 50 or 100 AGNs observed with Fuse, I don't know how to pronounce it, and the slope that they recover is this one, and I am simply adding it to my object. Maybe this can improve if I change the slope a little bit depending on the type of AGN, but I think that at the end is 2 points, and for me it is more important to get closer to the reality rather than having this all. So having the slope coming here or here is not going to change much with respect to the dramatic change as compared to what it was before. So don't forget that we are not trying to do physics here, we are trying to get the right redshift, or get as close as possible to the right redshift. Okay, so then after adding the power law to my object, and again, if you're using a code that does not have this component inbuilt, you don't need that component. It's only because LEFAR is working that way. The other very important point is the emission lines in the templates, because they improve on the photosys, even when only broadband photometry is used. So this plot was provided by Hilbert et al. 2006, where he was showing in orange the color as a function of redshift for spectroscopically confirmed galaxies, and in green, red, and blue you have the templates of passive normal galaxies and starbursts, and solid line is a template without any emission line, and the dashed line is for the same object with emission line computed starting from the UV part of the templates using the chemical relation and then recovering the emission lines from the, starting from the H alpha and adding back the oxygen lines, the Balmer lines, and the Lyman alpha. And you can see clearly how these features are better represented by the emission lines templates rather than the continuum one. And a lot of people say, yeah, thank you, you are here using here a color with a broadband and a narrow band photometry, or actually intermediate band photometry, but actually the same feature is visible also when you are using color based on broadband photometry only. Certain features or certain distribution in the color map for galaxies is better represented by the presence of emission lines. That's why I am having the emission lines in the host. Now, in the templates that we were using in Salvato 09 and 11, the host was coming from the Polletta templates. And if you're looking at templates of Polletta for normal galaxies, a lot of the emission lines have been cut and only the continuum kept, while the new paper that the new library that we have created with Li-Ting Su and Tony Manana take the hosts with emission line from a data set of Noll et al. 2004. And that's why you see in my hybrids a lot of the emission lines in addition to the AGN component. Once that you have the right templates, you then have to define your library, and this is the part that is extremely crucial. I'm using this plot from the paper of Bean in 2010 for expressing this point. What they were trying to do there was in the Chandra field south, they had 220 spectra that they used for then computing the redshift also for the rest of the survey. And using all the spectroscopic sample available, the spectra for all the objects, they managed to have only 1% outliers and an accuracy of 1%, which is fantastic. However, they pointed out that if you take the entire sample and you use 75% of the spectra for creating templates for then fitting the other 25%, the situation changed dramatically. The outliers become almost 9% and the sigma is 6%. And this is telling indeed that the templates that you are selecting are making the difference in your final result, which is something that is not true if you run the Hilbert library for normal galaxies in any survey of normal galaxy. They are going to work well, period. And here the problem is always that the relative contribution between the host and the AGN is unknown. So what do we do? We tried to explain what we do with this plot in, again, in Li-Ting and Tonima paper, where we plot the distribution of X-ray sources as a function of the X-ray flux for different surveys: pencil beam, very deep Chandra field south, and then the extreme, the XMM cosmos. And what you see is that XMM cosmos is practically lacking the faint sources of Chandra field south, and Chandra field south will have very little of the bright rare objects that XMM cosmos has. And in the moment in which you take this distribution and you normalize by the area of the survey, indeed you see that the bulk of the sources that are of this type are not present at all in XMM cosmos. So you really need to look at this kind of plot and understand which is the balance of different templates that you need to use for your sources. It's also important to remember that it is difficult to make this call just based on the spectroscopic sample that you are available, because the spectroscopic sample is not always representative of the entire population. So rather than running Photoz on the sample and then try to find which is the library balance, is really better, at least for AGNs, to use this kind of mapping and then see where your survey is going to fall in. So just to give you an example here, we add to the plot the stripe 82 which is again much brighter and much wider than what XM Cosmos was, and notice that the type of sources are the same that eROSITA all-sky survey will have. And so we made the prediction and we said, whatever library is going to work for STRIPE-82 is going to work also for eROSITA. And that is actually what is happening. So here I'm running the Photoz again for eROSITA in the IFEDs, and you see that if I use my old templates for the point-like sources, my accuracy and fraction of outliers is lower and higher with respect to the same results obtained using the library that we made for STRIPE-82. So better accuracy and a lower fraction of outliers. So the concept is actually really working. Once that you have defined your library, then you have the question on which kind of bands are best for your Photoz. Definitely we know from normal galaxies that the near-infrared bands are very important. This plot is taken from the Photoz review paper that with Hilbert and with Olivier and Ben we have made last year, where you see that normal galaxies have a higher redshift in Photoz if you compute only the Photoz using optical photometry, and you get the right one instead if you use optical and near-infrared. So near-infrared is important. However, also the U band is extremely important. I would say that for AGNs it is even more important, because in this very old plot, what I show is the luminosity redshift distribution for AGNs in Cosmos, computed with all the photometry available in Cosmos, and then I recompute the Photoz using only optical and near-infrared without the U. And what you see is that I am creating these orange sources that should not be there, because my white sources are indicating the right distribution at the moment. And only when I then add back the U band, then the distribution go back to be the correct one. So I'm very happy for LSST having the U band, because it is really important for our work. However, for me, is not the near-infrared photometry or U band a very important point. As long as you have a narrow and intermediate band photometry, I would say that these are the most important bands to have, because AGNs are characterized by emission lines, and the narrow and intermediate band key features. This plot is back is 11 years old, and I have shown here the results for Cosmos using different data sets. So here you have the point-like, here you have the extended, here you have the outliers and the outliers, and here the accuracy for the samples. And this is the result obtained using all the photometry available. And what you see is that as soon as I take away the intermediate and narrow band photometry, the outliers increase by a factor of 3, and the accuracy decrease quite a lot. While the accuracy and photometry remain practically the same if I remove IRAC, even if IRAC was very deep, just because these are the features. Intermediate band photometry is done in this paper, where we took a sample of star-forming objects at high redshift, and here you have the dispersion Photoz versus SPEC-Z, and you see how when you are using the intermediate band photometry, the peak is actually at 0, and higher the redshift, higher is the dispersion that you get if you do not use the intermediate band photometry. So definitely is important. We also demonstrate that is true for AGNs, not only in Cosmos, but other surveys. Here in the paper of Tonima, we have that all the X-ray surveys, those that perform better, are those that have intermediate and narrow band photometry in it. Again, here you have the accuracy and the outliers. So I would suggest that really we keep an eye on whatever survey can provide us with the intermediate and narrow band photometry. In this case, you have the JPAS. even if it is shallower with respect to LSST, for example, it is still providing a valuable information for at least the brightest object with bright emission lines. Most important, in the future, we are going to have SPHERICS, which is going to provide 57 narrow bands photometry in all, starting from the zeta band until W2, W3, if I remember correctly. And this is going to be great for the IREX universe of the AGNs.
But I mean, SphereX is like 15 arcsecond pixels or something. I mean, how many?
Yeah. So there will
you actually have useful information.
Yes. So I think this is one of the points that I have in the summary. We need to speak on apply unwise like photometry, so force photometry. It cannot simply be a match in coordinates. That is definitely one of the biggest problems. But you can already see in the legacy survey how good work can be done with forced photometry using unwise.
Sure. But you also, you need the AGN to be sort of the brightest thing in that pixel.
Yes.
And
sure.
that's a big pixel.
Yes, I totally agree. I still see a benefit. It's not going to solve all your problem, but I really believe that it is going to be really helpful, especially for the high redshift part, I would say. I really would like to have somebody from the SpheRX run some simulation. If you know somebody, it will be really interesting to see how they can do it. Finally, again, we have another.
Yeah, so Dan Stern would be my suggestion to who to reach out to, because he's at least at JPL and interested in similar science.
Yes, maybe we could also speak with Olivier Doré. Maybe having,
Olivier is of course in charge.
Yes, but having somebody that is working in LSST and SpheRX and interest in AGN, this will be definitely a nice master project, I would say. How SpheRX could improve LSST photometry for photosys of AGNs, for example. Finally, I would like to have another plot again on narrowband and intermediate band photometry, where we show that all the existing surveys that have intermediate narrowband photometry, these are those with the asterisks, are those that have the higher accuracy also at the faint end of the magnitude distribution. So I really think that we should keep an eye on this kind of data. Variability. As you know, AGNs are varying. Here I'm just showing two examples of XMM Cosmos sources that have Penstar light curves, and you can see how the objects vary in all the 5 bands of Penstar, and this is creating a problem when you are running photometric redshift, because the photometry is usually not coming as just one pass, but it is the sum of many observations in order to go deeper. And in this way, you are blurring the photometry, having actually a median value rather than the actual value. And in addition, it's not that you have all the bands run at the same time, but every band will be taken with different cadence and different length of time. So it's really difficult then to correct for variability. We tried to demonstrate this in an old paper of Torben Sim, where we took these XMM Cosmos sources with the Penstar light curve, and we computed the photosys in 3 different ways. The first time we took the photometry coming from the closest possible dates in time, so that the variability will not be an issue. Then we took the photometry obtained as the median value of all the photometry available for that object over the years. And then in 2 different executions, we took random bands representing again 2 possible ways of gathering photometry for large surveys. And as you can expect, the best result is of course obtained when there is no time lag between the various photometric bands, even using only optical photometry from Penstar without any additional bands. So I really believe that LSST will not have this issue, but actually you can compute good photosys, and not only that, you can even flag the sources knowing that they are going to be varying so that you can apply some prior where then you are computing the photometric redshifts.
Just a comment, Mara.
Yeah.
I mean, LSST will have this problem too.
Not necessarily, right? Because one pass is going to be anyhow deeper than anything else before. It is a problem when you want to add all the years together. But if
but LSST's one pass is going to go to 24th magnitude, but we really are going to want to go to 27th magnitude in the deepest.
Yes, sure. But at the moment we are at 21 magnitude, we want to go to 24. So yeah, up to 24, you do not have the problem.
Yeah.
So of course you have it if you want to go, you are pushing further the problem, I would say. I am already happy to be saved by the problem up to magnitude 24, which is the magnitude for many of the AGNs that we are detecting, at least in X-ray at the moment.
One thing.
So how long elapsed? Sorry, go ahead.
No, sorry. One thing to know about that, so it's still not clear what the cadence between the different bands will be in the general survey, so that will definitely have an impact. But I think also the fact that we can probably model a lot of the variability for these sources will allow us to put those priors you were mentioning, Mara. So
yes.
I think LSST,
so what do you mean with modeling? This is something that I'm interested. What do you mean with the modeling?
So for example, seeing how variable is a source can have some information about its luminosity or its ratio. So
sure.
that would
but it's not that you can predict. Yeah, sure. But it's not that you can predict how it is going to vary, because I was showing here, this guy was flat for many years and then started to go up. Years go down, up, and then flat. So it's that you cannot predict. But yes, probably we are going to learn now properties of the AGNs as it depends on how they are going to vary with some machine learning and such. And then this can be then used as a prior for computing the Photoz. Totally agree with you there. So this will be another project to investigate.
Yes, I had a related question, which is how long a time lag can you allow between the different bands to effectively have a simultaneous SED to a fit from? Is a week different okay? Is a month different okay? 6 months? When does it become untenable?
Again, it depends on the survey that you are using. The most affected objects are the bright, which are rare. So if you have a very deep pencil beam small, the objects are few of that type, so it doesn't matter really the cadence, so it is affecting you less. Cosmos was affected a lot. So here is a plot on an object that was varying during the time in which we took the observation with for XMM Cosmos, and you can see how the variability actually increased. So the object became brighter, and you can see here, this is the photometry that was taken with Sloan, and this is our photometry over a few years, over 3 years. You have different symbols. The green is the photometry after the correction for variability. I think that this is a kind of answering to your question, Jeff, is because the planning of the observation is crucial. So we got lucky. At the beginning, people were not interested in AGNs when we started to work on Cosmos. It just came up later by luck. So what they have done is that every time they went to the telescope, they have observed a set of filters that were covering the entire range. And in this way, we really got the variability all over the optical range with the passing of the years, rather than going deeper in R band or deeper in I band, focusing first on the red bands and then the blue band. In this way, we really had the SED, the tracking of the variability of the entire SED. And probably this is something that with LSST can be done. So that then, as long as you are able to trace how the object have changed in all the photometric points, you can correct for it. So this is how we did it in Cosmos. We pass a running filter through all the points, and for all the points, then we took the mean value of these. Sorry, just to say also that our points were not the sum of photometry taken over the year. It was really the photometry taken at that point. So then we use the mean value of the points over the entire SED. So again, we have demonstrated before that this is not optimal, but at least it was working.
And so if you calculate photoz's from two different epochs with different spectra and average them, do you get a better photometric redshift overall? Do they contain separate information?
I'm writing down this question because it is a good one and I never tried. Let me a second, I write.
Sure.
Okay, thanks. Okay, I will try to look into it. Okay, so then I discussed all the key points in the. I have only 4 minutes to go. I have all the machine learning to go through. I'll try to accelerate. I'm really sorry. So what about machine learning? The machine learning people say the people working on SED fitting are limited because they are relying on a physical relation, while we prefer to ignore that. And I think this is a wrong attitude because implicitly they are using the same color redshift mapping and they're just simply pretending to not know it. So this is the plot that we use for explaining the concept. You have the templates, you have the two filters, you have a feature, and then you look at how the feature is behaving along the redshift depending on the templates that you are using. And what we have done was then, one of the limitations of the machine learning is that despite being advancing fast, they are really strongly depending still on the training sample, but above all, they are limited by the completeness of the photometry. What we have done in this paper is we took all the data that were used for the Ananda paper and tried to compare step by step how we could improve the photosys using machine learning. And the first limit is already here. In the sample, we have almost 6,000 AGNs. And if you want to have a photometry in all the bands, you are down to 1/3 of the sample. And you can then try, like Ruiz have done, or we have done, then rerun the training using less photometry for another subsample, less photometry, another subsample, and then put the pieces together. But as I will show you later, still you don't manage to get a value for all your sources. So if you wanted to run a luminosity function of your object, you are going to miss really the value. However, machine learning have some capability that we should consider when we are running our photosys. So here is the continuation of what I just said. We run the photosys only with Sloan, Sloan and VHS, Sloan and IRAC, Sloan and WISE, and then different combinations. This is the optimal, where you have the objects for all, the photometry for all the objects. And indeed, you see how this result is better than the merged sample, for example. Accuracy and fraction of outliers, which is actually better than what we have obtained with the CD fitting. Although,
so one thing the machine learning methods can do is incorporate things besides color, like variability or structure function information. So has anyone tried that to see if it's informative on Redshift?
No, we did not do that. It is another good point. I am happy to provide you the Cosmos data with or without variability correction. And sorry, in this experiment, we could not run it because we do not have variability information for stripe 82. This is stripe 82, which has a 31 square degrees. So we wanted to go wide and having broadband photometry only, simulating what Erosita will see. And
yeah, people have variability statistics for stripe 82.
Yeah, right, because of the supernova stuff. You are right. So this is something that could be used. So this is another master project, if you like, that I am happy to help you with. Definitely not something that I can run, but it's definitely interesting to take into account the variability and see how this can help. You are absolutely right. I didn't think to it. Yes. One thing that is important to do with machine learning, or what things that I have learned at least, is that some of the information that we are providing is redundant. And you don't need to, you actually make your results worse if you use all the information that you have. So here is an example, again, for the same sample as before. If you limit if you make an analysis of the important features using only photometric points, you can get good results using just the first 4 or 5 bands. And if you are using magnitude and colors, again, you can limit yourself to the first 6, 7 part and ignore all the rest, which is actually negligible. And here you have the results of the photosys computed using all the photometry and all the features. And then you see how using the best features in the MAG color, optical color MAG distribution, this one, the accuracy is actually improving with comparison before. So smaller fraction of outliers and a higher accuracy. So definitely making an analysis of the feature is very important. This is one of the code that can do that.
Was that random forest or what code was
this is no, is it is like this MPQLNR, which is the code that we are using here. Is I forgot in this moment.
We can talk later.
Yeah, you can find it out in the actually in the paper here, Brescia. We have a section that summarizes what the metaphor is based on.
Okay.
The other thing that was important to see is how we can improve on the photosys applying the same criteria that we have used for the SED fitting, at least for the extended sample. So this is the best that we could obtain using the feature analysis. And the result here is split in extended and point-like. Here you have the MAD and the fraction of outliers. And you see how splitting the sample, so having a training sample for the extended sources and a training sample for the point-like is actually at least improving dramatically the extended one. Then probably some of the sources should help. Maybe our separation was too sharp, and you can see here that result is not very good, and in average the result is only slightly better. Actually is only a little bit less outliers. I mean, practically it's the same. The only improvement here is on the extended part, which is the galaxy dominated one. So of course, splitting the sample, you improve on the results. The other problem that with machine learning have at the moment is that they are using photometry without the photometric error. The people that I spoke with say they tried to use the photometric error, but it doesn't improve things. And I think that the problem is that they are using the photometric error as an additional column rather than binding it to the photometric point. So somehow the photometry should be photometry plus minus the error, so having a range of value rather than just a range. And I think that in that way, the photosys will improve also for machine learning. And what we have done here is showing how limiting the sample to object with a good photometry in all the bands actually improve the accuracy. In general, if you have the same data, if you have a photometry in all the bands, and you have a good training sample, maximum machine learning is already now providing photosys that are better than the CD fitting. There are no the systematics that you get from the CD fitting, for example, but again, it is only a limited number of samples. So this is 1/5 of the entire sample that we had available in the Stripe 82. It is not a problem of peculiar objects that we are not able to represent. It is really a limitation in the method that we are not really understanding yet. So here you have the redshift photosys computed with machine learning versus SPEC-Z, and photosys via CD fitting and SPEC-Z, and photosys via machine learning and SPEC-Z. And color-coded in orange, you have the outliers of SD fitting, and in cyan, the outliers from the machine learning. And what you see is that very few sources are outliers in both methods. The other are really related to the code that you are using. It means that probably merging the two methods or comparing better the two methods can teach us how to interpret the outliers, because they are not outliers, is a limitation of the method that we are using. Final, before spending 2 minutes on a final point, is the PDZ. You know that in order to compute maximum luminosity functions, you need to have also the redshift probability distribution function. And the PDZ for SED fitting is normally extremely narrow and very picky. And the recent attempt in computing PDZ for machine learning are actually broader. Here you have the real value of the zeta spec, Photoz from LEFAR, Photoz from machine learning, and the 1 sigma error and 1 sigma error. And we know already also from the paper of Dahlen, where we were mentioning already that often our sigma error on the Photozs are too optimistic, and they need to be enlarged in order to be more realistic. It is a problem of the entire PDZ in reality. And you see it here in the outliers, in the histogram of the PDZ for the outliers. The machine learning does not dare to assign a PDZ higher than 50% or 80% depending on the photometry that is available. While LSD fitting is convinced that about the 50, for 50% of the outliers, it is still convinced that the PDZ, that the redshift that we're assigning was the right one, which instead was extremely wrong. So I really think that we have to learn to trust less the PDZ coming from SED fitting, at least when the photometry used for the Photoz is only broadband photometry. Last point, which is then bringing back to what I would like to propose as MPE to LSST, is what if we have an AGN in the sample and we did not know that it was there? Here you see the AGNs in Cosmos treated as galaxies in the catalog of LIGO 2016 compared to the Photozs that we have computed in Marchesi, knowing that they were actually AGNs. And you see how dramatically change the accuracy and the fraction of outliers. For the galaxies, you have many times that you are not even able to assign a redshift. And in Euclid, we have made an experiment. In the challenge of the, for the photometric redshift for Euclid, what has been done was taking the Cosmos survey, cut it in half, use half for training and half for testing. And I did not tell to the people that there was that there were AGNs in the sample, and inside there were AGNs selected in optical, different way of selecting. There were power law IRAC selected AGNs. There were the WISE AGNs of Roberto and Nick. There were the X-ray AGNs, and there were the radio AGNs. And this is just an example. And you see here what is happening. In that half of the sky, there were 778 AGNs with spectroscopy. And we have 192 wrong and 25% of the sources have the wrong Photozs. Here we have that almost more than half have the wrong Photozs when you are running Photozs for power law AGNs. Here for the bright quasar, probably the effect is less because you use the Lyman alpha for identifying the object. Actually, these are low redshifts, so this doesn't work as explanation. Somehow this sample was well represented and at very little outliers. For the sources of Roberto, again, more than 50% of the sources were outliers and so on. So it means really that the AGNs are everywhere, we know that, but they are affecting our results. And what we want to do is actually flag all of them to clean up and allow the people working on other scientific cases to get a cleaner sample, and for us working properly with all the type of AGN and finally understand how they are working. And the final point is that a lot of people know that the objects are an AGN, but then they use the stellar masses and the stellar masses coming from the fitting as they were normal galaxies at the redshift of the normal galaxy. So it is completely wrong what it is done. And once that you have identified that object is an AGN, you need to run the Photozs as they are AGN, and you need to do the SED fitting for the physical parameter of the host as it is an AGN with an AGN component. So I think that these are very important points if you want to do science also with LSST. So I am done. Actually, it took 43 minutes without the questions, so I'm in time. And what I discussed is that the spectroscopic sample for AGNs is getting larger and larger, which is good, but it is still biased toward bright objects. It means that we still have a need of photometric redshift for AGNs. We know how to compute a reliable photometric redshift, either via machine learning or SED fitting, but we need to work more on the quality of the data that we are using more bands, trying to collaborate with groups that can provide the intermediate band photometry, for example. And the important point here is really try to get photometry that is speaking to each other, and a simple match in coordinates is not sufficient if you want to do a good job. Finally, we want to flag AGNs everywhere so that they can be treated properly, and at the same time, the science done for non-AGN project is going to be much better. And this is all what I wanted to show to you. Thank you for the attention.
Oh, thank you very much. That was a really, really interesting talk. I think we already interrupted you a lot during the talk. There's a lot of questions, and I see already.
It was a pleasure. It's much nicer in this way, believe me.
And I think there's already a couple of questions. So I'll keep recording the questions. We typically allocate an hour for this telecon, so people may have to drop out, but we can look at the questions later. So I guess see JT has Schindler has a question. Maybe we can start with that one.
Sure. Yeah. Hi, Mara. Thanks for the very nice talk.
Thanks for listening.
I was curious. So the highest redshift objects that I saw in all of your plots were around redshift 4. So, and it's probably because of the samples that you selected. Can you easily extend your methods to redshift, say 5 and 6, with the templates that you currently have, or do you need to sort of build new templates for this?
The answer is yes, I can, but I cannot tell more because there's going to be a paper about one of the first high redshift objects detected by Rosita, where we got the redshift right using my templates and my method, and it is confirmed spectroscopically.
Okay,
I cannot say more at the moment.
Okay, I was just curious. So you basically have templates that incorporate the random forest, the Lyman alpha force, and all of these physical things that happen to the quasar spectrum.
Yes, correct. This was again training on the stripe 82 that has the right depth in ancillary data, and X-ray data was very important for getting the right templates to use for Rosita. Yes.
Okay, and so just a quick follow-up. So with my experience on photometric redshift, there are certain quasar types that really are troublesome. For instance, broad absorption line quasars can mimic quasars at very different redshifts. And so have you encountered issues with these objects? Have you excluded them from your selections, or how have you treated them?
I do not exclude them, also because a priori you do not know them. I have Markarian 231 that try to represent all of them. I'm actually trying to test in the next days the library of Michel Brown, which has a more complete library of AGNs. I just needed to add back the power law that it does not have, and he has many more of these strange objects, and I wanted to see whether I can improve using also those. But at the moment, the strongly absorbed objects are better represented with the Markarian 231 from my experience.
Okay, thank you very much.
No problem.
All right. I think Il-Sang Yun, you also have a question?
Thank you. Thanks for the talk. You mentioned the importance of U-band observation, but also I was wondering, because as you know, LSST the U-band has very different observing cadence compared to the other bands. And unless we really know what LSST going to do with the U-band, I think, have you ever considered a sort of simulation whether because the U-band, the amplitude and the variation of the U-band, the amplitude and the time scale of the U-band variations might be very different from other bands. For the given data set, have you ever considering a simulations of U-band differently compared to the other bands, and how that difference will affect your photo Z determination?
I did not do that because my experience with the U-band comes from Cosmos, which was treated equally in the other side, with the other bands. This again could be a project that we can develop together. Again, as I was telling at the beginning, we needed to define better our proposal in how to contribute in kind to LSST. And this could be, for example, a project that we can develop together. I do not have an answer at the moment.
Thanks.
I will say that because the U is the area, at least in the area where the objects are going to be varying the most, it is really important to know how the cadence is affecting your results. So maybe using Cosmos again and pretending to have a U band obtaining different cadence and then rerun the Photoz, how this can change. This could be something that we could try. Yes.
Thanks.
Yeah, I guess one thing that, it kind of building onto that could be very useful is to determine how deep U has to be compared to G. I think we're still trying to, there's still going to be a lot of fighting about the cadence, but I think it's a fairly good assumption that U is not going to be as deep as G, for example. So it would be good to see how deep, or as a function of depth of U compared to G, for example, how good Photoz improves, so we can at least fight for a specific number in that, that ratio.
So for example, in Cosmos, we have that all the bands are more or less 26 magnitude AB, including the U. And maybe we could reduce the sample. Maybe what we could do is, since all the data are available, we could actually create different depths of the U bands and see how this is affecting. The plot that I've shown on the effect of the U band creating a lot of, the lack of U band creating a lot of interloper at high redshift is done with the depth of Cosmos. So I do not know, we need to work in order to make it what happens when it is shallower.
Okay. Franz, I think you also have a question.
Yeah. So, I mean, I think you've demonstrated over the last decade that AGN it's important to take them into account when dealing with Photoz, and they are an important source of outliers. Another important source of outliers, which I feel has not been strongly recognized or dealt with yet, is dust-obscured galaxies and dust-obscured AGN. How do you see us tackling that problem?
It's not a problem in terms of Photoz, Franz. It is a problem if you want to do science about AGNs. If the goal is to compute...
No, it's a problem with Photoz.
No, I agree with you. Sorry, because I put it as last line. I didn't speak about extinction. You're absolutely right. If you do not have the right extinction, you are not creating the right template. You're absolutely right. Good point. You need to have a sample of a highly obscured object with spec Z and see how is it working.
Yeah.
So we can try to create one using all the X-ray data that are available now on surveys for which we have the photometry. So all the obscured objects in stripe 2 with spec Z, all the obscured objects in Cosmos or any other survey, and then try to run it there and see how the result change. You are absolutely right. The one thing that is also important to do is sometimes we forget is that we are using all the training sample for then also as a tester, and we should not do that. I think that now we have enough spectroscopy in order to split the sample in two and see what is happening on a blind test.
Yeah. That's the approach that machine learning people have been
they
taking
do,
for
absolutely.
years, because
absolutely.
it leads to overfitting, and they know that it leads to overfitting.
Absolutely.
Yeah, and in that sense, actually, things with medium obscuration may be the most complicated, right? Where the blue looks like a galaxy and the red looks like an AGN.
Yeah, but then the hybrids that I'm creating could do the trick, right? Again, we are not trying to create something that makes sense physically. We just want to have the right features to identify the redshift. And as long as we get the feature right, who cares for the rest? Then, of course, you have to, once that you have the redshift right, you do the right assumption and you do the determination of the physical parameters using the right component. When you run the Photoz, you just want to be able to grasp the right feature.
Yes.
And this is particularly important for the machine learning. They don't care about the SED.
Mm-hmm. I'm really sorry. I think I'm going to say your name really incorrectly, but Swayam Trapta, you also have a question?
Thanks. Yes. So I just want to follow up to the first question that Franz had for the alpha UV. So I understand in Scott et al. They do have the mean alpha UV at minus 0.56, but there is quite a dispersion in the value for them, and they are not. And when they do a division of the sample based on luminosity, they have a low luminosity cutoff 10 to the power 45. They do get variance in the alpha. So I was wondering how would that impact the estimations that you showed us, especially from the SET point of view?
I will wonder, I am curious as well. I can try to have a different slope. I think that at the beginning, 11 years ago, I could go back on my directors. I experimented with different slopes. And I think that at the end, this was giving me the best results. But again, it is always depending on the population that you are trying to fit. So it can be that because of the depth of X-ray cosmos and the size, the typical objects are more represented by that type of power law, and another one would work better in another survey. So, but this definitely makes sense to try other power law slope and see if this is affecting the photosis.
Thanks.
I'm writing down all what you are saying because it can be that I'm going back to you and propose this as part of our contribution to the working group.
Yeah, absolutely. And I think Gordon has a question as well.
I have more things to discuss, so we can close up and I can send more an email. But just so people know, I was interested in talking more about both the UV spectral index, DCR, and kriging of light curves with errors. But I think it may be longer than we have time for here.
Yeah, I think so. This is nominally supposed to last for an hour, so maybe.
Sorry.
No worries. No, it was fantastic.
No, that's great. Yeah, I'll send you an email right now. So.
Okay, great.
Okay, thank you. So before closing, sorry. So in the email that we received from the LSS team, they are asking us to get in contact with the